Okay, so in the previous video, I went and showed you basically the 8 properties we need to form linear combinations. So let's just jump into the definition again. You'll notice it's exactly the same as the previous definition. The only thing actually changed was the objects we work on. Notice that in linear combinations, those 8 properties are all we need to manipulate things. That's what's actually important. What the actual objects are that's being added and subtracted don't matter, actually. Don't really matter. So we'll say if A sub 1, A sub 2 up to A sub k are all the same size matrix, and C sub 1, C sub 2 up to C sub k are just real scalars, we can then form a linear combination of this form. We then call the scalars the coefficients in that linear combination. They're also sometimes called coordinates, if we make some other assumptions. A matrix A is then said to be a linear combination of other matrices if it can be expressed as a linear combination of these matrices, A sub 1 up to A sub k, just for some choice of coefficients. This is the exact same definition we had before with vectors. It's just now with matrices. So just as an example, I want to know, is the matrix 1, 5, 5, 3, reading across the rows like that, 1, 5, 5, 3, a linear combination of these 3 matrices? Well, we have to find out then, is there some linear combination of those 3 matrices that adds up to the matrix 1, 5, 5, 3? So let's just go ahead and start by saying, let's just find them. Let's just find some scalar where it works. And if we can't find scalars, then it is not a linear combination of those 3 matrices. So let's try to find scalars C1, C2, and C3 so that is true. Well, the left-hand side and the right-hand side, they're both matrices. So if 2 matrices are equal, that means that corresponding entries are equal. So on the left-hand side, just add it all up. Just multiply everything out and add it all up, and you get that thing. Those 2 matrices have to be equal to each other. That means then just by writing down corresponding entries being equal, you get these 4 equations. So then if this matrix 1, 5, 5, 3 is a linear combination of those 3 matrices, then that linear system in C1, C2, and C3, it has to be consistent. So let's find out if it is. Let's see if that system is consistent. We now have a linear system. We know how to handle those. We just take that linear system and we put it in as an augmented matrix and we row reduce it. I did it all at once for you there. I actually gave you the row reduced echelon form of the matrix. From that row reduced echelon form, you can then pick off instantly what C1, C2, and C2 have to equal. And actually, there is only one answer. That's great. All we need to know is there an answer? So if there's more than one answer, great. All we need to know is there an answer? Is there a choice of scalars, C1 and C2 and C3? And there is. In fact, if you just write it down, you see that the matrix 1, 5, 5, 3 is 3 times the first matrix minus 1 times the second matrix plus 2 times the third matrix in the 3 matrices that I gave you. So the answer is yeah, that matrix is in fact a linear combination of those 3. Now, once you have linear combinations, though, we can then launch into spanning sets and linear independence, because those are both defined in terms of just everyday normal linear combinations. So I'll go through this a lot faster because this is the same work, really. We'll say then the span of a bunch of matrices is a set of all linear combinations of those matrices. So I want to know then, is the matrix 1, 5, 4, 3, is that in the span of these 3 matrices? Well, when you say is something in the span, you really mean, is this something a linear combinations of the matrices that form the span? So we just have to find scalars, C1, C2, and C3, so that this particular linear combination equals 1, 5, 4, 3. Once again, we just add the left-hand side, get the exact same thing we have on the left-hand side. That then once again, just by comparing corresponding entries, that gives us these 4 equations. And we just want to know now, is this system consistent or not? If it's consistent, then there is a choice of scalars so that the matrix 1, 5, 4, 3 is a linear combination of the 3 matrices I gave you. If it's not consistent, then there are no such scalars, which means that 1, 5, 4, 3 is not a linear combination of the 3 matrices I gave you. And that would then mean it's not in the span. So let's just check to see if that system is consistent or not. To do so, just like I did before, I have the system. I write down the augmented matrix. I then row reduce it, and I look at that augmented matrix. I notice though that there is a leading entry in the last column. Anytime there's a leading entry in the last column, that system is inconsistent. The very last row there says 0 equals 1. So that's clearly not true. So there can't be a C1, C2, and C3 that makes all 4 equations true. Otherwise, if they were all true, then the last equation, 0 equals 1, is true, which it's not. So then no. Since that system is inconsistent, that means the matrix 1, 5, 4, 3. Oh, on my slide here, I have 5. So that should be 1, 5, 4, 3. That thing is not a linear combination of the 3 matrices I gave you. So the matrix 1, 5, 4, 3 is not in the span. And I think that's enough for that video.